So lesson 14 is cubic equations and inequalities in context. 14 or lesson 14 kind of separates it into three different sections where they do 14.1 is the writing the equations and inequalities, and then 14.2 is solving, and then 14.3 is interpreting. We're just going to kind of jumble that all into one. So we'll write an equation, solve it, and then interpret it. Okay, so example one. Eileen constructed a rectangular open paper box. She first cut equally sized squares from the corners of a sheet of paper that measured 17 inches by 23 inches. Then she folded up the sides. So we took like an entire piece of paper. You can see the picture on the right side, but an entire sheet of paper that was 23 inches across and then 17 inches like down or tall, however you want to view it. And then she cut equally sized squares from the corners. So that's these squares right here. We don't know how big those squares are. We just know they're equally sized. So since we don't know what they are or what their size is, we'll just use X to describe them. She cut those squares out so that we could actually like kind of fold up the paper box as opposed to just like having a flat piece of paper. And then next we want to write the equation of the function that represents the volume of the rectangular box. Volume is like how much we can hold within it, where X represents the length of one side of the square. Okay, so because we had to cut the corners out. I wish I could like physically hold this paper in front of you, but each of these sides are gonna fold upward. So this part right here, this part right here, this part, this part. So they're all gonna kind of fold up into, picture like an open topped box. It's not gonna have a lid on it or anything like that. So once we fold all those sides up, they're not going to be, 23 inches across and 17 inches down. We have to take into consideration the like corner squares that we cut out, and they do that in the graphic for us. So if we start with a like width of 23, and then we take off X and we take off another X, we're doing 23 minus 2X. So that's where that comes from. And then if we have a length of 17, but we're cutting off X and X from each side, then we end up with 17 minus 2X, so that's where that comes from. So for the like actual dimensions of our box, we're not using the 17 and the 23, we use the 23 minus 2X and the 17 minus 2X. And then the volume formula is V equals length times width times height. So we can go ahead and just put all of our dimensions in there. We don't know the volume yet, so I'm just gonna leave that as is. So V is equal to length, I'm gonna say, and it doesn't really matter which one you make which necessarily. I'll say that the length is the 23 minus 2X. And then times the width. So we'll say 17 minus 2X. And then the height, so if we like are folding up the sides, these are going to be our heights, like the X like dimension that gets folded up from each corner. So for times height, it would be times X. So volume is just all three kind of like dimensions or sides multiplied together. So 23 minus 2X times 17 minus 2X times X. And then we just want to simplify it and get it into standard form. So if I want to get it in standard form, I'll just start by foiling these two. It doesn't like, there's not a set order that you have to go in, but I'll just foil those two and then I'll distribute the X in after. So bring down my V equals, and then it'll be 23 times 17 is 391. So this will go in parentheses since I still have that like last X that I'll have to multiply in also. So 23 times 17 is 391. And then next is 23 times negative 2X. So it'd be a negative 46X. And then next is Negative 2x times 17, so that would be a negative 34x. And then next would be negative 2x times a negative 2x, which would turn into a positive 4x squared. And then close parentheses and then bring down your x. And then before we distribute the x in, we just want to like combine like terms so there's less steps for us to do once we distribute the x back in or in general. So we have a negative 46x and a negative 34x that are like terms. So we'll combine those. I'm going to rewrite this up here. So v is equal to, and then, oops, I think I might have said the correct product from set 23 and 17, but I don't think I wrote the right one. So 23 times 17, yeah. I don't know why I wrote 393. It should be 391. So if you wrote the 3 with me, change it to 391 right there. And then, so it'll be 391. And then now I can combine the like terms. So negative 46 minus 34 is negative 80, so minus 80x. And then next I just have to bring over my 4x squared, so plus 4x squared. And then times, close parentheses, and then times x. And then from there, we'll just distribute in the x. So I'm going to kind of do this backwards because I want it to be in standard form. So that means like the exponents go like from highest to lowest. So it'll be v is equal to, I'm going to do the x times 4x squared first. So x times 4x squared is 4x cubed, and then x times negative 80x is negative 80x squared, and then x times 391 would become plus 391x. Okay, so we have the equation now, v equals 4x cubed minus 80x squared plus 391x. And then the next section is solving. So if the volume of the paper box is 563.09328 inches cubed, what is the side length of the square? We're going to solve using a graphing calculator. So if it asks for the side length of the square is just x. So we don't have to like do anything special to find it, we just have to solve for x. So we're saying that the volume is 536 point something something something. We're going to take that whole thing and put it into the v part of our equation because that represents volume. So what that's going to look like, it would be 563.09328 equals 4x to the third power minus 80x squared, and then plus 391x. So when we're solving cubic functions, sometimes you can factor. This is not one of those times, but if you had something that like, you could factor by grouping, you could technically solve by factoring. This is not the case here, so we're going to use a GeoGebra graphing calculator to solve. So when we use the calculator, and I'll kind of show it on the screen as well, but basically what we do is we type in the word solve, and you'll see like a solve function pop up with parentheses, and then we type this entire thing into parentheses. So you'll see me do it. I was gonna kind of like have it pre-entered, but I feel like it's helpful to like see it typed in, so it just may take a second. Okay, so go to the page. It should say like geogebra.org/classic, and I'll link it, of course, like on the notes page and stuff. But you'll see we can start typing in solve. Hopefully it worked. Yeah, there we go. So yeah, sorry. So you can see now it says solve. Click on that, and then click on where it says solve parentheses equation. And then now we're going to type in our entire equation. So go back to the numbers. It was 563.09. Hopefully I don't mess this up. The number or the buttons are pretty small. 0.093 2, 8, and then the equal sign, and then 4x, and then if so on mine, like I have the button for an exponent. If you don't on yours, let me see if it's on here. Yeah, you would hit the like little up arrow button like that. I don't know if it'll work since I have the option for exponent, but if you're typing on a computer, you'd hit that to put in the cubed or any exponent in general. And you get that by clicking Shift 6, like holding Shift and then pressing the 6 key for that little like up arrow above it. I'm just going to click the exponent button, so 4x cubed, and then minus 80x squared, and then let's see, oops, I went too far, and then plus 391x. Okay, you should already like kind of see that parentheses like around the backside. You don't need to add like a new one that's got taken away for some reason. But now below you can see like within like kind of like brackets, it says x equals 3.22, another x equals 3.22, and then x equals 13.55. Those are your solutions. So we're going to take those. I'm just going to copy them to the other page. So we ended up with x equals 3.22, and then x equals 13.55. Okay, and then now we just have to make sure that those numbers actually like make sense in the context of this problem. Like not even just like make sense, but make the length and the width of the rectangle work. So I'm gonna create like kind of like a little mini table. So my height, I'm gonna move this down a little bit actually, give myself more space. Okay, so my height was x, and then my length was 23 minus 2x, and then my width was 17 minus 2x. And I just have to take both of my solutions and actually test them and make sure I get something that makes sense. So let's say for x equals 3.22 first. So if I plug that in for just x, that would just be 3.22. And then if I do 23 minus, if I put the like 3.22 in here, it would go here and then here. This would be 23 minus 2 times 3.22. So if I do 2 times 3.22, it's, I don't know why I'm doing that with the calculator, but I just don't want to mess it up. 2 times 3.22 is 6.44. I feel like that was easy enough. But we'll do 23 minus 6.44 is 16.56. So this is 16.56, and then we do the same thing with the width. So 17 minus 2 times x. So 17 minus 2 times 3.22, so minus 6.44. It's 10.56. So 17 minus 2 times 3.22, that all simplified is 10.56. So there's nothing that's like a very like blatant like issue here. So we're good. I'm gonna fix that 10. It doesn't really look like a 10. It's a little bit better. Okay. And then now we just need to check our other x value that we got. So like the other x value that we got was 13.55. So x equals 13.55, so that would make the height 13.55 because the height was just x. And then this would be 23 minus 2 times 13.55. So 13.55 times 2 is 21.7. So we do 23 minus 21. I already forgot the number. It's 2 times 13. 2 times 13.55 is 27.1. And then if I subtract that from 23, I end up with negative 4.1. And then for the width, it would be 17 minus 2 times 13.55 goes in for x this time. So 2 times 13.55 was 27.1. And then if I subtract that from 17, I get negative 10.1. So we have to think about what these like numbers are supposed to represent. Like they're supposed to represent length and width. And you can't have a negative length or a negative width because those are distances. So that x equals like 13.55, it is like a solution, but it's not really like valid in the context of this problem. So it's called extraneous. So extraneous, in case you've never seen the word before. It just means that the solution that we're going to focus on is the 3.22 because that was what gave us like realistic length and widths. For the next part, Eileen wants the volume of the box to be less than 563.09328 cubic inches. She creates a graph to see what the options are. So we're trying to find domain and range for this problem, and usually for cubic functions, the domain and range is all real numbers. In this case, though, like if we're dealing with volume and like length, width, height, it doesn't really make sense for all real numbers to work because that includes negatives, and we can't have a negative volume or like a negative length, width, height, etc. So we can find the like kind of actual domain and range by looking at the graph. So before we get started with the graph, I think there was a typo on it because it said like cubic feet, or yeah, in cubic feet or in feet. I'm pretty sure it should be inches, just like from what's in your workbook. So the original problem had like a sheet of paper and it was 23 inches across and 17 inches down. There's no way we could take that and make a box that has 550 cubic feet in volume. So just keep in mind there's like that little mistake in your workbook. Okay, so in order for us to find the domain and range, we want to like look at what parts of the graph are actually kind of like valid for this problem. So we need our volume to be positive. So if we look at the like y-axis, that's the volume of our graph. So having a positive volume means that our function is positive. So it's all the sections of the graph that are above the x-axis, so that part, and then this part over here. But because of this middle section where it goes and dips down below the x-axis, like in this middle section, the volume is negative. So we can't have a negative volume. So that means that we can't really pay attention to any part of the graph that happens after that. So this part we're not looking at, or that part. We're only focused on like kind of that initial kind of like curve there. So for where it's positive between this point and this point. And we can certainly like estimate these points, but we also have a way of finding them out for sure. So I'd rather us just find like the exact values. So those are the zeros. So we would want to find the zeros of the function. And before we do that, we'll go back up to like the original equations that we set up to decide which one would be better to use. So we have this one right here, that's the function in standard form. We could find the zeros of it. We'd have to probably use a graphing calculator to do so. We also have it right here, and that's in factored form. So if it's in factored form, then we can just use the zero product property to set each factor equal to 0. So we don't have to use a calculator for that. So we'll just go ahead and take that one. I'm going to take it and copy it down below, and then we'll use that to find the zeros / the x-intercepts. Okay, so if I want to find the zeros of the function, that means that I put 0 in for, in this case, v. Normally it would be like f of x. But in this case, it's v. So we'll write our equation as 0 equals 23 minus 2x times 17 minus 2x times x, and then it's already in factored form, so we could just set each factor equal to 0. So first we'll do 23 minus 2x equals 0. And then next is 17 minus 2x equals 0. And then the next one is just the x equals 0. It's always easy to forget about like the little like kind of individual or like singular term factors, but we can't forget about those. And then now we solve each little equation for x. So this one I would subtract 23 from both sides. And then I bring down the negative 2x, and then equals 0 minus 23, so negative 23. And then if I divide both sides by negative 2, I get x equals 11.5. And then for the second equation, I would want to get x by itself, so I would subtract the 17 over. I would bring down the negative 2x, and then 0 minus 17 is negative 17. And then if I divide both sides by negative 2, I get positive 8.5. And then the last one, I don't have to really do any solving. It was just already x equals 0. So those are all of our 0/x intercepts. So if we go back and look at the graph, we can see it crosses through at 0. And then that's telling us that this is an exact 0 or x-intercept at 8.5. We maybe could have estimated that, but you can just never really be sure. And then there was that third one at 11.5 right here. So that 11.5, like it is a 0, but we just don't like really need it in this context because of this part of the graph that dipped below, makes the rest of this not really matter for this problem. So for the domain, it's like what x values or input values are giving me a positive volume. So it's between 0 and 8.5. So our domain would be between 0 and 8.5. We'll write it in interval notation, then just remember it's not like a point. We're saying the x values, like the possible ones for this problem, are between 0 and 8.5. And then for the range, it's kind of the same idea, but we're looking at the height of the graph. It says estimate. I don't think we really need to estimate. It might have just been a typo on my part. We can just find it. So the range is like kind of what's the possible height of the graph. So for our volume, like kind of the lower limit would be 0. It wouldn't be like able to be 0 or anything below it. And then the upper limit is right here. And it looks like we have to estimate that point, but not really, because it says that Eileen wants the volume of the box to be less than 563.09328. So that's going to be the upper limit of our range. Our range will go from 0 to that 563 number. So range will be between 0 and 563.09328. And then interval notation, remember just putting either parentheses or brackets around it, but like the volume can't actually like be 0, so we want to include 0. And then we want it to be like less than, not less than or equal to, so we would put the parentheses around the 563 as well. And then for the next section, this is the last little part of like at least this problem, and there's one little problem after it. Not little, I guess, but there's one problem after it. So analyze the graph to the right to determine the different options to keep the box under a volume of 563.09328. Basically, oops, I wrote on this and forgot to erase it. Basically, any point on this graph, so notice like we kind of took away the parts of the graph that don't really matter for this problem away, and we just have like that initial part where the volume was positive. Basically, any point on this graph would work, because any point is going to be, as long as it's not just like this point right here, any point that's below it is going to have a volume that's less than 563.09328. So we can pick a few different points. Like if we pick this one, that would be with a side length of 6. And remember, this is a typo also, so it should be 6 inches. This should be cubic inches also. So if the box, or the little, not box, but square, has a side length of 6, it would have a volume of, I'm gonna estimate that at 330. or like another one, and these are just estimates, they're not going to be perfect. Let's say right here, if it had a side length of 0.5 and then a volume of 170 cubic inches. And the point of this is just like, any point on the graph that's below that maximum would work, and it would give our box a volume that's less than that 563. For example, 2, Dietrich is constructing a rectangular paper box. He will make the box 8 inches wide, and the length of the box is 3 inches more than its width. The height of the box is 5 inches more than its width. So considering the possible values for the volume of the box, right, and solving an inequality, it helps find the possible values. So since it's a box, we use the same formula we used before. That's like the formula for a rectangular prism, which is volume equals length times width times height. And then they tell us, it looks like in the second sentence, they start to kind of tell us how to describe our length, width, and height. So it says he will make the box X inches wide. So our width is going to be X, and then the length is 3 inches more than its width. So for length, we would do X plus 3 for 3 inches more than the width. And then the height is 5 inches more than its width. So for the height, we would do X plus 5. So we'll take all of those and put them into the formula. So width X, and then length X plus 3, and then height X plus 5. I'm going to put the X out in front though. So we'll do X and then times X plus 3, and then times X plus 5. And when it says consider, like, or considering the possible values, it's kind of gearing towards getting us to write like an inequality as opposed to an equation, because we don't know the actual volume. We just want to describe like every single possibility. So volume just has to be positive. So we would write our inequality as greater than 0. So X times X plus 3 times X plus 5 has to be greater than 0. It's just our volume has to be positive. So that's why that whole thing needs to be greater than 0. And then now we want to take a look at the graph at the right and determine what our actual like solution set would be for this problem. I just want to talk a little bit like how we would find that graph. So I know it's there for us, but the equation, or sorry, inequality that we set up is in factored form. So it's pretty easy to find the zeros. We would just set each factor equal to 0. So we would do, well, not equal to, we'll just do equal to for this case. Even though it's an inequality, I just need to find what the intercepts are. So one would be X equals 0, one would be X plus 3 equals 0, and then one would be X plus 5 equals 0. So this would end up being X equals negative 3. This would end up being X equals negative 5 if we subtracted those over. And then you can see those on the graph. So like we have an x-intercept at negative 5, at negative 3, and then at 0. And then the rest of the graph could be figured out with like end behavior and stuff. I'm not going to go too far into that. But if we analyze the graph now, like the input value, like kind of not, yeah, our input value, the x, was our width. So that means that like all the x-axis, those are all our possible values for width. And then the output value, that was what we got from like multiplying all this together. That was the volume. So that means that our y-axis is going to be the volume. And if it doesn't make sense to have a negative volume, then only like a very limited part of our graph is valid here. So we can't have a negative volume, meaning like this whole section of the graph all the way back here. We also can't have a negative width for that matter. So this whole section, like all these parts that have a negative width and especially negative volume, those aren't a part of the solution set for this specific problem. Even though like they're on the graph and stuff like that, we have to think back to like the context and stuff. So the only part of the graph that is within the solution set for this problem would be this section over here. And just relating it back is like, that's the section of the graph where the width is positive, and the volume is positive. So for our solution set, it would be like starting at 0 and then everywhere to the right of it. So it would be between 0 and infinity. And of course, like depending on the size of the paper, like the volume like is limited. It's not gonna actually go up to infinity, but we don't know the size of the paper, so we can't like really put a limit on the volume at all. So we just have to think like, okay, width has to be positive, volume has to be positive, so our solution set is just all of the positive values.